No batteries, just gravity. Let's go. Okay. This time we're going to talk about angular velocity. So hopefully that was a nice little demo of angular velocity. Let's hop into the math of it. All right. So before we can talk about angular velocity, we have to talk about the thing that angular velocity changes. So we know that velocity changes the position of an object over time. Angular velocity causes changes in position. Sorry, not position. Oof. Angular velocity causes changes in angle. So theta. So this thing theta is the way we keep track of where we are in a cycle of rotation. So for example, let's say that I'm spinning a yo-yo with my hand. I don't remember if Patrick had a similar video, but let's say I'm spinning a yo-yo. So here's my yo-yo, boom. All right. Now if the yo-yo is spinning around this pivot point, I'll mark it with a PP, pivot point, spinning around with some speed, which I won't label as speed, but I'll just instead say it's going around. All right, it's going around. Now, as this yo-yo, here's a string connecting me to the yo-yo. As this yo-yo is going around, the thing that I say is changing is its angle, so it's theta. So typically, by convention, we define theta to be measured relative to the positive x-axis. And as time goes on, my angle is going to change. My angle is going to change as I go around. So here, it looks like the angle is maybe, let's say, 60 degrees. As it rotates around, it'll come up to 180, 270, and back to 0. Okay, may seem trivial, but the point is that omega gives us, the angular velocity, gives us a measure of how quickly this theta is changing and in what direction, like clockwise or counterclockwise, and along what axis. One other thing I wanted to hit on while we're here is that solid bodies can only rotate around a single axis. Let me get a quick example for this. Okay, so I've got here some duct tape. So if I take my duct tape and I spin it, here we go. It's only rotating around one axis. It's only rotating around, in this case, the vertical axis, the z-axis. So if I were to put my finger here and try to spin it, I could probably get it to spin on top of my finger. I'm not going to do it because it's going to take me too much time. But here's a spin again in the air. So it's mostly rotating around the z-axis. Now, that axis doesn't have to be constant in time. In our case, we're going to pretty much always have constant in time axes. So we're going to have nice, simple rotations where our axis stays constant. But you can imagine something like wobblier. So an example of this is a thrown football. You didn't throw quite right. So if you throw a football, so an American football is what I mean. If you throw a football and you throw it a little bit off kilter, you'll find that as it rotates, it wobbles. So the axis around which it rotates changes. We'll talk a little bit more about footballs in a second. But in here, typically you can assume that the axis stays the same. The axis of rotation stays the same. Okay, the other thing I wanted to dig in on here is this notion of pivot point, because I think it throws a lot of people for a loop, especially early on. So a pivot point is a section, it's a point in a 2D picture. A pivot point is a point that does not move. So it's a point that does not move over the course of the rotation. If I want to get really, really, really explicit, a pivot point is just some origin. It doesn't have to be a point that doesn't move. But in our case, it's always going to be a point that does not move over the course of rotation. So in that seesaw example from last time, the deal was that all of the other points along this seesaw, along this orange board that I'm about to draw, all of the other points over the course of a rotation move except for the pivot point. So the pivot point is the thing that doesn't move. Another typical example of a pivot point, always good to mark with PP. Another good example of a pivot point is the center of a CD-ROM. So if I have a CD-ROM, am I dating myself? I feel like everybody still knows what CD-ROMs are. If I have the center of a vinyl record, okay. So the center of a CD-ROM, as it rotates, I'm only 26, you guys. I'm not that old yet. Pivot point, as it rotates, this center point of a CD doesn't move. All the other points throughout the CD are going to move around it as the CD rotates in its usual way. Okay. Now, here's the part that I think tends to lose people. So if this doesn't make sense and these previous two things made sense, you're probably good to go. a pivot point in 3 dimensions is really an axis. So if I've got a football, say, boom, we're making it a green football for some reason. It's COVID season. Maybe it's been collecting mold somewhere and is now green. If I've got this green football, now if I throw this football the right way, then hopefully it only rotates around an axis that cuts directly through the center of the football, like this. So it makes contact with the skin at the tail and at the tip, and then it passes through this inner region that is mostly empty, right? The part of the football that's mostly air. So all of these points along this little axis are pivot points in the sense that they stay in the same place during the rotation. All the points outside of them are going to rotate during this rotation of this football. Let's say the football's rotating this way. Okay, around the pink axis here. So, as I say in the slide, typical uses, I wanted to include the notion of a seesaw. So sometimes I have a fixed pivot point. Another example is like a door. So a door is fixed at the hinges. For objects that are not like fixed, they tend to rotate around their center of mass. So like if I just rotate my what is this thing called? My tape, it'll tend to rotate around a point right in the middle of the tape. So I'll do it one more time. And if I rotate it this way, same deal. That was probably, I probably need to put in a headphone warning there. All right. So it rotates around the center of mass if there's no fixed point. Okay. I think that's all I really want to say for pivot point. So the pivot point is the main, I would say the main new thing that doesn't really translate that well from linear momentum. So getting used to pivot points is a good idea. All right, now we're finally there. We can talk about angular velocity. So on the way to talking about angular velocity, we're also going to have to discuss the right-hand rule, which is a sign convention that we make in physics to talk about whether things are rotating clockwise or counterclockwise. So what is angular velocity? First off, what are its units? Let's write it down. Omega, angular velocity. The units of angular velocity are radians per second. Radians per second. Now, radian is not actually a true unit in the sense that, like, there's no such thing as like a conversion between energy and radians, for example. Radian is not an SI unit. It just means, you know, the way that we measure angles when 0 means nothing and 2 pi means I go all the way back around. So units of radians per second, in terms of like actual physical units, it's just 1 over second, which I know can be really confusing. So typically we'll keep it as radians per second. Okay, so with units of radians per second, a radian is kind of like a degree. It measures some angle that I've gone through, that I've gone around. Per second tells me that it's a rate. So it's a number of radians that I go around in a certain amount of time. So this tells me how quickly an object rotates around an axis of rotation, So what I'm going to do is I'm going to take my archetypal example of a CD, and I'm going to try to draw it in 3D. Here we go. Boom. Nice, dude. Okay, there's my CD. There's the center of it. Okay, so say that my object is rotating this way. My CD is rotating this way. It's rotating around this axis, which I'll mark in light blue, that passes directly through the center of the CD. So the pivot point of the CD is right there in the center. It rotates around this light blue axis. And as it's rotating around, let's say that it spins at, I don't know, call it 10 rotations per second. 10 rotations per second. Okay, so it's spinning at 10 rotations per second. One rotation is 2 pi radians. So that could be a good conversion to remember. One rotation equals 2 pi radians. So if my object is spinning at 10 rotations per second, that tells me that the magnitude of my angular velocity is 2 pi times 10 radians per second. So that's going to be 20 pi radians per second. Cool. That's telling me how quickly this disk is rotating around this pivot point in the center. So omega is a vector, right? Omega is a vector. So we have to talk about what that vectorness means. Like, what does it mean for omega to be a vector? Angular velocity tells me not only how fast it's going, but also what axis it's rotating about and in what direction. So omega always points in the direction of the rotation axis, either up or down in this case. And whether it points up or down depends on what we call the right-hand rule. So this is a sign convention that we make in physics. So here's the rule. Take out your right hand. Here we go. And what we're going to do is we're going to put our palm at the pivot axis. We're going to put it at the pivot point. And I'm going to take my fingers and make sure they curl in the same direction as the rotation itself. So the direction that my thumb points tells me the direction of omega. Okay, so here omega points up. Omega. Now, because the right-hand rule tends to throw people for a loop, I want to show an example, like really be explicit about why it is that way and not the other way. So if I line my fingers up, my right fingers up with this direction of motion at the edge, you can see here's my pointer finger, my middle finger, my ring finger, and my pinky. Nice. Then as my fingers are going around, my thumb is going to be pointing up. So my thumb is pointing like this. Whoa, all right, wow. Not the best hand I've ever drawn. My thumb is pointing up. If you don't trust me, try it for yourself. So I've got this object. It's rotating this way. Here we go, it's rotating. I take my right hand, put it in the direction of rotation, and then put my fingers in the direction of rotation, and then use my thumb to determine whether the vector for angular velocity is pointing up or down. In this case, it's up. So there you go. Now, two other things that are important. The first thing is a little memorizational thing you can use to check yourself for the right-hand rule. So I recommend just learning the right-hand rule straight up, but if when you're first learning it, it's hard, here's a memorizational thing to help you out. So if I'm viewing my object, say it is a clock now, just for convenience. That'll make life easy. So if the hand is moving clockwise, if it's moving the way it normally does, i.e. like to the right from the up position, then down and around like this, then I say that my my angular velocity, omega, is pointing into the page. Into the page. So x means into the page. Into the page. If it's rotating counterclockwise viewed from above, so viewed like this, CCW, then omega is pointing out of the page. Out of the page. Okay, the way that I personally remember which one's into the page and which one's out of the page between the X and the dot is like an arrow. So if I'm shooting an arrow, if I'm making the shot myself, if I'm the archer, then what I see as I shoot the arrow away from me are the feathers. Right? That's the thing that's closer to me. So I see that little hash of the feathers. If the arrow is coming towards me, if I'm the hunted, then I see the arrow. I see the pointer. So that's how I know that the arrow is coming toward me, is I see the arrowhead first, the dot. So that means it's coming toward me. Okay. Okay, so again, right-hand rule. What does the right-hand rule say? The right-hand rule for angular velocity says that the angular velocity points in the direction of my thumb when I take the fingers of my right hand and curl them in the direction of rotation. So notice that angular velocity points perpendicular to the actual individual velocities of any point on the surface. It makes an angle of 90 degrees with any of these individual velocity vectors on the surface. The last thing I wanted to say, this is like, I would say it ranks like number, it's very low on the list of equations that you should know, but just to kind of link angular velocity to angle, the rate of change of the angle in radians is the angular momentum's magnitude. So if I have a constant omega, if I have a constant angular velocity, the change in angle is omega times delta t. So if I know that something is moving 2 pi radians in a second, 2 pi radians in a second, then after 1 second, here's my object, it's rotating this way. This tells me that if after a delta t of 1 second, and again, let's be super explicit, omega equals 2 pi rad per second. After 1 second, it'll have made its way all the way around and back to its starting point. So this is delta t equals 1 second. Make its way all the way around. Woo! Came back to itself. Okay, so in this example then, omega would be 2 pi radians per second. Delta t would be 1 second. So my change in angle is 2 pi, which takes me all the way back around. Okay, sweet. I think that's it for this video on angular velocity and the right-hand rule. Up next, angular momentum and moment of inertia.